Hi, this video is here to help discuss some of the basics of probability and counting problems. This video is going to cover some topics about probability. There will be other videos to talk about, say, the addition rule and a few of the other topics that we'll discuss a little later in the course. I have prepared a short number of slides just to help aid with the discussion. All of the examples, for the most part, are coming out of our textbook. So you'll see very similar things in the sections dealing with counting and probability. Here is the table of contents, just a little overview of how this video is going to run. First, we're going to talk about just definitions for a few things. Then we'll use some of those definitions to understand the fundamental counting principle, in particular, how we can use that principle to count the possible number of outcomes, the total number of outcomes possible. And then we'll calculate some probabilities using both the classical and empirical methods. There is a third type of probability known as subjective. I will speak about that, but we won't really look detailed into any examples. We don't spend much of our class looking into subjective probabilities. Then we'll get the definition of what the complement of an event E is. And we'll look at conditional probabilities and the multiplication rule for both dependent and independent events. So lots of definitions, a few rules which are sometimes thought of as formulas, so some good things to take notes on here. So starting with some of those definitions. A probability experiment is when we have an action which results in we get some specific results. Those results are called outcomes. One particular, just one result would be one outcome. So an outcome is the result from a single trial in a probability experiment. And then the sample space is what we refer to as the set of all possible outcomes. So just to work in a brief example related to these terms, these new definitions, we can create a sample space or illustrate the sample space for people's blood type and talk about how big that sample space is or how many possible outcomes are there. So people's blood type, they can have letters that refer to the blood type, but also we have plus and minus or positive and negative. The positive negative refers to the Rh factor. So there are four main blood types. There's type O, type A, type B, and type AB. But each of these four blood types contain people who are Rh positive, so O positive, or Rh negative, which would be O negative. So each of the four blood types has two blood types actually held within it. The A positive and A negative, both coming from the A blood type, the B negative and B positive, coming from the B type, and then the AB negative and AB positive coming from type AB blood. So this sample space, this is all possible outcomes. If we were to randomly select people and look to see what type of blood they have, it would be one of these 8 types listed at the bottom. So this sample space is the set of blood types O positive, O negative, A positive, A negative, B positive, B negative, and AB positive, and lastly AB negative. So there are 8 possible outcomes in our sample space if the probability experiment has to do with blood types. So just getting an idea of what these things look like. This type of drawing that I've used here is called a tree diagram. We use tree diagrams in some cases, especially if the amount of choices is relatively limited and small. Like here, there were only 4 blood types, and then each of those types had a positive or negative Rh factor, totaling for 8 types altogether. Sometimes, though, the numbers are much larger, and it will be inconvenient to try and draw a tree diagram. So for small case stuff, drawing is a great way to understand the set of possible outcomes. Another term, another definition, is the word event. So an event is a subset of a sample space. So it means some of the possible outcomes, but not necessarily all of the possible outcomes make up an event. You can have an event where it's just one outcome, meaning it's a simple event, or you can have an event where it's more than one outcome, where we have more than one outcome possible, so it would just not be a simple event. We would not call it simple. If we're unable to list all possible outcomes, and we need a way to count up how many, we use what's known as the fundamental counting principle. So the fundamental counting principle is stated here in the red box. It's also found in your books, roughly page 132. And it states that if we have a series of choices to make, in the definition in the red box, we're talking about just having 2 choices to make, but you can extend this idea to having 3, 4, 5, however many choices. But if we have a series of choices to make, we can choose M options for the first choice, and then there are N different options for the second choice. We can talk about the total number of ways the sequence of events can happen is M times N, where you're just multiplying the number of ways for choice 1 and times the number of options for choice 2. I'm going to illustrate that principle a little bit here with this example found in green on the slide. So you're ordering a 3-course meal, and you want to count the number of possible different meals that you could order from the menu below. So there are 4 options for an appetizer, 4 options for a main dish, and 3 options for dessert. So we could, in these numbers 4 and 3, these are pretty small numbers, so we could, in theory, make a tree diagram for this. We would have 4 options for our appetizer. I'm not really going to draw the whole tree diagram, because I think, as we'll see, it gets a little too full. But we could have the wings, the soft pretzel, the nacho, or the onion ring. And then after deciding one of those 4, we then would have 4 options for our main dish. So from choosing wings, there would be 4 main entrees. We'd have a burger, a BLT, we could have a pizza, we could have tuna, right? And then we'd see that same 4 options repeated for each of the nachos, the soft pretzel, the onion rings. And we would need to grow this tree diagram even one layer further because there is a third choice, dessert. So if I chose wings for my appetizer and burger for my main dish, I could choose either ice cream, pie, or cake for my dessert. And then each of these other options would have 3 branches coming off of it. And I think you can see how big and unmanageable this tree starts to get. So instead, employing the fundamental counting principle is going to be the preferred method for most cases. So we'll have our choice of app times our choice of main dish times our choices for dessert. And that is 4 choices for appetizers times the 4 choices for the main dish times the 3 desserts. And when you multiply those together, there are 48 different meals that could be chosen from this menu. I think that this example illustrates well how we can pick, how we can total up and count up all the ways our outcomes could be, how many different outcomes there are. So there's 48 different outcomes in this sample space, where with the blood type, we only had 8 different outcomes. So with that information in place, we have the fundamental counting principle and a lot of definitions. We're going to look into probabilities. So there are 3 types of probabilities. We will look at the classical, or theoretical is another word for it, the classical probabilities in some detail with an example. We'll look at empirical probabilities. So that's also known as the statistical probability. We'll look at an example with that as well. And the third type is subjective. At the beginning of the video, I mentioned how subjective probabilities are not really something we're going to study in depth in our class. So I want to talk a little bit about what those are, then we'll look at the formulas for the other 2 types. A subjective probability uses intuition and educated guessing and estimates to come up with a likelihood, a probability of an event occurring. For instance, we see this with sportscasters. They like to say things about predicting winners of different contests. Like, for instance, a sportscaster may say the Yankees this year have a 35% chance of making it to the World Series, or something along those lines. So that's coming from the sportscaster's natural intuition towards sports from their experience, but also some educated guessing using things like statistics about the team currently, guessing what it will be like in the future when the World Series comes up. So that's subjective. We see it also with like doctors when we hear doctors on TV shows and things say, oh, the patient has a 95% chance of surviving the surgery and things like that. It's all based on an educated guess using the information available. We are going to calculate and not guess so much. So we're not really going to use these subjective probabilities, but we might see them when we come across things that we are reading. As far as calculation goes, that's where we're going to use either the classical or empirical probability approach. So the classical theoretical probabilities, we want to use this option if each outcome is equally likely. So if the outcomes that are possible all have the same likelihood of being our result. So when we have a case where all the outcomes are equally likely, we find the probability of an event E happening by dividing the number of outcomes that would say, yes, event E happened, by the total number of possible outcomes. So we can see already, I hope, how the fundamental counting principle might help us to determine the total number of outcomes possible, for instance. All right, so with an example for classical probabilities, here you have a 6-sided die. It's a fair die. You roll it. What's the probability that you roll a 5? So I would talk about that as P of 5, but you read this, instead of saying P of 5 like we do for functions, we read it as the probability of rolling a 5. And the probability of rolling a 5, how many ways can I roll a die and have the number on it be 5? There's only one way. I roll it and get a 5. So that's my numerator, the number of outcomes in E, just the 1. Total number of outcomes possible, well, I could roll a 1, a 2, a 3, a 4, a 5, or a 6. So there's 6 total number of outcomes possible. So we can say that the probability is 1/6. There's a second probability question asked here as well, and we'll use the classical approach as well, because when you roll a die, it's equally likely to land on one of the numbers as it is any of the other numbers. So find the probability you roll less than a 4. So if you roll less than a 4, there's 3 ways you could roll less than a 4, right? You could roll a 1, a 2, or a 3, and those are all less than 4. So the probability that you roll less than a 4, and maybe because this is not for a single number, I'm going to put roll less than 4 inside my parentheses. The probability that you roll less than a 4, there's 3 ways that could happen out of the 6 total outcomes possible, because you could technically roll any number, 1 through 6. So our probability of rolling less than a 4 is 3/6, or if simplified, 1/2. So this is classical probabilities, calculating classical probabilities of a single event happening. If we have a situation where the outcomes are not equally likely, so not something where we're rolling a die, but something else, we will want to use a different method. So if they're not equally likely, then we're going to use the statistical probability or the empirical probability. The empirical probability is made based on observations from some probability experiment. The equation for calculating is actually our relative frequency equation from back in a previous chapter when we talked about frequency distributions and relative frequency. So the probability when we do not have equally likely events, the probability of event E happening is equal to the frequency of event E from some probability experiment, somewhere where we already went and collected data. The frequency of that event E happening divided by the total number of frequency, which is just the relative frequency of E in that probability experiment. I'll zoom in a bit here so that we can really see the graph. But we're asked to find a probability based on the information in this pie chart. So this pie chart is found on page 135 in our book. The pie chart shows how 1,502 adults have been surveyed and asked, how did you read books in the last year? So 409 said they read no books. 560 people read only paper books printed. 425 read both printed and digital books, and a little over 100 people read only digital books. So if we're asked to determine the probability that the next adult you survey will have said, I've only read paper books. So we can agree just based on how the pie chart is split up. It doesn't look like these events are equally likely. So I'm going to use that empirical approach, which means the probability of only paper books is equal to the frequency of only paper books. So that's the number of people who had only had paper books, which would be 560 people, out of the total number of outcomes, the total frequency here. And that would be the full amount of people surveyed, 1,502. And you could arrive at that number because it's told to us, or you can make some additions here and arrive at that number as well. So if we divide 560 by 1,502, we're going to see our probability of, I'll round to 3 decimal places, roughly 0.373. So you can interpret probabilities as fractions, as we did in the previous example about rolling a dice. You can also talk about them with decimals. And a lot of times when we're discussing them in interpretation, students are more comfortable using a percent to talk about this rather than a decimal. So it's roughly, the sample had 37.3% of people roughly give this result. That would be the relative frequency, 0.373 or 373 thousandths. A few basic concepts and another definition coming from the first section in our chapter on probability. We have the probability of an event. Any event will always be a number between 0 and 1. It is allowed to be equal to 0 or allowed to be equal to 1. So you should never see a probability that's a negative number, and you should never see a probability larger than 1. If a probability is equal to 0, then that would mean that that has like a 0% chance of happening. We have no possibility. It's an impossible outcome. If a probability is equal to 1, actually equal to 1, not just close, that's like saying there's a 100% chance it's going to happen. So then we are very, very sure. In fact, it's a definite outcome. So very rarely would you see probabilities equal to 0 or equal to 1, because it has to do with things where we're already certain, essentially. Most of the time, the probabilities will be somewhere in between. Back to the slide. The sum of the probabilities for each of the outcomes in a sample space is 1. So for instance, with rolling the dice, if we have a dice, the sample space is that you could roll a 6-sided dice and arrive at one of 6 numbers. The probability, let's have our roll number, and we'll make like a little probability table here. So the probability of rolling a 1 is 1/6, because there's one way to roll a 1 out of 6 options, total outcomes, and this is a classical approach. For 2, 3, 4, 5, and 6, in fact, the probability is 1/6 for each of these. So if I look at the entire sample space and I add up all the probabilities, the summation is equal to 1. So we do, in fact, have that instance. That happens both for situations where we have equally likely outcomes, like rolling a die, but also in other situations where the outcomes are not known to be equally likely. The last definition to discuss is the definition of the complement of an event. So we've been referring to events as capital letters like E, A, B. The complement of E is written as an apostrophe. We say it E prime, or complement of E. And because a probability experiment should have a sum of all possible outcomes probabilities equal to the number 1, Complement means not. It's the opposite of E. So if our event was in rolling a dice, if our event was rolling an even, call that E, then E prime would be not rolling an even or rolling an odd number, right? They're opposite. And because all of the probabilities add up to the whole number 1, if we know the probability of rolling an even or whatever event E is, we can use subtraction. 1 minus that probability will tell me the rest of the probabilities. So that's how one way we can find the complement, just by using 1 minus the probability of the event happening tells us the probability the event does not happen, which would be the complement not happening. Okay, we have completely discussed the first section of our probability chapter at this point in the video. There's a little more discussion that comes up from the material found in section 2. So we're going to talk about conditional probabilities. Usually you won't be asked to compute a conditional probability on its own, but you'll use it as a part of finding a probability for something using the general multiplication rule. So we need to understand what a conditional probability is so that we understand how and when to use the general multiplication rule for probabilities. So let me get the definition back up. So moving to the next slide. A conditional probability. So a conditional probability is a probability of an event happening given that some other event has already happened. And we write about it using this vertical bar. So P parentheses B vertical bar A. We would read that as the probability of event B occurring given that event A already happened. So I have an example here using a deck of cards. This is your standard playing cards, 52 cards in the deck, 4 aces, 4 kings, 4 queens, 4 jacks, 4 tens, etc. We're having our 4 suits with 13 cards each, so 52 total cards. So from that standard deck of playing cards, we're asked to find the probability that the second card chosen is a queen, given that you already chose the first card and it was a king. So that king did not get replaced back into the deck. Because the first card is a king and it's not replaced back in, when we're picking the second card, there's only 51 cards left in the deck. We took 1 king out already. Of those, so there's 51 cards that we have to pick from for our second choice. Of the 51 cards, 4 are queens. And with choosing cards at random from a deck, we are able to compute our probability of event B given A, meaning probability we choose a queen given a king was already chosen, as the 4 queens that are possible out of the 51 cards remaining because 1 king got taken out already. So we get 4 over 51, or roughly 0.078. So that's computing a conditional probability. I had to take into account that it was no longer 52 cards, so that denominator was affected, which changes the fraction overall, which changes the probability overall. So with this conditional probability stuff, we're starting to look at a sequence of events occurring rather than just a single event. It's important when we have more than one event to consider if one event affects the probability of another event. And that's where we come into our last new definitions for this video, the definitions of independent and dependent events. So when you have more than one event, so here we're describing just for 2, but when you have more than one event, they're considered to be independent if the occurrence of one event does not affect the probability of the other event happening. So A and B are independent events whenever the probability of B given A is equal to just the probability of B, or phrased the other way around, the probability of A given B is equal to just the probability of A. And to see an example, perhaps, where events are not and are independent, with the deck of playing cards. The first card pulled out was a king. The second card, we wanted to know what the probability was we would get a queen. So that was a series of two events. First event, pulling a king out. Second event, and then not replacing it, not putting it back in the deck. And then the second event, pulling the queen out. So we actually have events where they are affecting each other. Those would be dependent. They are not independent. For an example of events that are independent, perhaps you are going to flip a coin and then also roll a die. If you're going to flip a coin and roll a die, whether your coin is heads or tails makes no impact on what number you get from rolling the dice. So we have independence there. Depending on if they're independent or dependent events, changes which version of the multiplication rule we will use. So starting from independent events, where we're tossing a coin and rolling a dice, two things that really don't affect the outcome of the other. We can just simply find the probability for each event separately and then multiply them together. So here is the equation statement for that multiplication rule that I just described in words, and then an example beneath. There's a coin and it's tossed and a die that is also rolled. So we want to know the probability that you toss a head and then you roll the 6. So the probability of heads and 6 is going to be equal to the probability of getting a head on your coin toss times the probability of rolling a 6 on your die. Both of these events are taking place in a situation where all the outcomes are equally likely when you look at them separately, right? When you toss a fair coin, you have a half or 0.5 chance that you're going to get heads, half that you'll get tails. With the dice, you have 6 different numbers. Each of them has a 1/6 probability. So my probability of heads would be one outcome is heads out of 2 possible outcomes, heads or tails. So 1/2. And for the dice, we have a probability of rolling a 6. There's only one way we get the number 6 out of 6 possible outcomes. And then we can multiply those together, and that is 1/12. So our probability would be 1/12 or 0.083 if we're rounding to 3 decimal places on the fraction, the decimal version. So that is the multiplication rule when our events are independent. If the events are not independent, then one of these changes a little bit, and we use the conditional probability rather than just probability of event B. So let me pull the last example. Here's our multiplication rule for dependent events. So this is like the playing cards. So we have a deck of playing cards. We pull out 2 cards, and we want to know the probability that the first card is a king, and then we also pick a second card, and it's a queen. So there's 2 different events happening here, and the multiplication rule changes slightly because these events depend on each other. So probability of A and B would be the probability of picking a king, and then after that, choosing a queen. So we'll find that probability by first talking about the probability for the first card we chose. What's the probability? We pull one out of the deck and we get a king. After we have that, we're going to multiply not by the probability of choosing a queen, but the probability of choosing a queen given the fact that a king was already chosen for the first card. So for the probability of choosing a king, you have 52 cards. 2 cards are selected without replacing the cards. We're not putting anything back in once we pick it out. So at the start, there are 52 cards. So there are 52 possible outcomes. How many ways can it be a king? Well, I could find the king of diamonds, the king of hearts, the king of spades, or the king of clubs. So there's 4 out of 52, or 4 over 52 would be our probability. For choosing a queen, there are 4 queens. We've already picked a king out, because it's assuming you've already had the king happen. So there's 4 queens, so there's 4 ways I could get a queen, but because I took that king out, there's only 51 cards left. So I would multiply these 2 probabilities together. That's 16 over 52 times 51, which is 2,652. Or in decimal version, that is 0.006 rounded to 3 decimal places. So the likelihood is close to 0, but it's not impossible because it's not exactly 0. But that would be finding our probability for some dependent events using this multiplication rule. Last thing I want to point out is that there is this word "and" between our events. We're looking for both events to happen. If the situation changes and you're asked, or, what's the probability you pick a queen or a king? It would be a different rule. We wouldn't be using the addition rule. We would use the addition rule rather than the multiplication rule. That is something that's going to come up in a separate video later on. I hope this was helpful. If you find there's other topics, even if it's things we've covered already in the past that you would like some short videos about, please feel free to email me and just send me your requests. As long as my schedule allows for it, I will find the time to make the videos and post them here on YouTube. Thanks. Bye.